We're going to cover in this section the Maxwell-Boltzmann curve, okay, which basically proves that temperature increases the rate of chemical reaction. Now, then I'm going to start talking introduction to chemical equilibrium. I'm not going to get into the nitty-gritties in this one because we probably won't have time in this section. So let's look at the Maxwell-Boltzmann curve. All right, let me put it back to black, and let's look at this. It's the Maxwell-Boltzmann, Bolt, like Boltzmann curve, okay, or the Maxwell-Boltzmann graph. Now, in your textbooks, you will see a curve that looks something like this. All right? I am going to explain that, and I am going to explain this. Okay, I just want to get them drawn first. Okay, and I want to put in a few little labels over here. All right, let's put it in over there. All right, and I've got here kinetic energy, EK, kinetic energy, okay, which is a measure of temperature, right? Which is, and a proxy for that is measuring temperature, right? Oops. Temperature as well is kinetic energy, isn't it? Okay, I'm going to label this as EA over there. I'm going to label this one over here in red as T1 and over there as T2. And now we're going to talk fraction or percentage of molecules. Okay, fraction or percentage of molecules or atoms, all right, depending on what it is, and kinetic energy, and there we've got our curves like so. There we go. Now, all I want to do now is I want to do this. If we went and we drew we said what we're going to do is we're going to plot frequency, okay, over there, all right, and over here, let us say class interval, right? This is a statistics curve, right? So what I'm going to do is I'm going to say, all right, I'm going to go around and I'm going to measure, for example, heights or lengths or widths of certain things, right? I am going to get, as a measurement, I'm going to get some over there. Then I'm going to get some over here, right? And we're going to build up a curve that generally looks like this, aren't I? Okay. Okay. And whatever these will be, 0 to 2, 2 to 4, blah, 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 blah. So I count the number. I get a frequency curve. Okay. And then what I do is I say, all right, I'm going to put a line of best fit between the middle of those, and I'm going to call that my graph, right? Like so. Now you can see that what I've done is I've got a smooth curve joining it. I have joined the center of my frequency polygons over there. Well, how does that relate to the top one? What I've done, if I now go back down, let's just go and examine our thing. What I've done here is I've said, all right, this here represents the energy of molecules. Some of them have got very little, some of them a lot. But remember, if I added up the sum of the frequency must be equal to my sample size, right? Because I'm adding up all them, that must be the total number of things I measured or temperatures I took or whatever. Or the frequency could even be times. How long did it take to boil this or that, or whatever the case might be. As such then, right, each one of these points on the line over here essentially represents the temperature or the energy of a specific atom or molecule. This point over here, okay, where I've measured, this is, if you like, the average. All right, let's give it the other name, the average, all right, or, oops, sorry, the average or the mean, all right. Now on the red one, I'm keeping the average or the mean. There we go. Let's call that the mean or the average. Okay. But now, the last thing to remember is that the area under the curve is equal to total number of molecules or atoms in the experiment. So the area under the black curve and the area under the red curve must be the same, right? So what we're saying is then the areas under the black curve and the area under, so the area under the black curve, okay, area under the black curve must be equal to the area under the red. I'm actually going to write that in red. Area under the red curve, right? Because it's the same number of atoms or molecules involved. All right? That's what's inside my pot. I've put them in there. Okay? Now, what it's saying is under natural conditions, okay, under natural conditions, my blue line here, this piece here, is my activation energy. So you can see that over there are few, and when I change it, there are many. What am I saying? If you look at the area underneath to the right, this is the few, that area there, and the new area 2 I'm going to explain below. So you just keep your curve there. All right? So now let me go back here. Okay, do it in blue. So area 1, okay, is the number of atoms or molecules that have an energy, an actual energy above EA. Right? They have actually got enough energy, therefore they can react. Right? In other words, they are in the activated complex zone. Anything above there is the activated complex zone, right? All right. Let's call it that there, shall we? Over here, this is the activated, let me just take this down. I really wish those buttons were a little more sensitive, but sadly they're not. Okay, let's take it down so that it's out of the way. Activated complex, just tidy my own writing up here. This is the activated complex zone, isn't it? Anything this side is the AC zone. So you can see there are few that are actually in the AC zone over here. But as the temperature goes up, more become part of the activated complex zone. So the area 2, all right, area 2, there are more in the activated complex zone. Therefore, more able to react. Correct? The last thing you have to know about this graph, which is very logical, okay, is just to explain, kind of run out of colors, so I'll just go back to black. I need to explain why that is down. Okay, it's simple. If you take, I don't know if ever of you have taken a panna cotta or a jelly or anything like that that's been set. If it's in the mold and you take it out, it flops. Okay, the same volume of stuff, but when you take it out, it slumps down. Okay, for those of you who are going to do engineering, you'll do slump tests on concrete and things. What it means is that it sits in this container, and when I tip it out, it flops, it slumps. All right. What has happened is I had this and I've pushed it over. I've actually done that with it, right? We've squished it to the, in this case, to the right, and we've pushed it down because the area must be the same under them. Okay? So the peak must fall when you draw it. That explains that Maxwell-Boltzmann curve. Okay? Let us now continue, all right, just recapping this endo and exothermic. Let's have a look, and we say over here, I'm going to, oh, no, I'm not going to put that there. I'm going to have A plus B going to C plus D plus delta H. All right? Well, what does that mean? It means that this is my reactants. This is my cooking zone or my activated complex. This is our products. So what did we do? We got heat given off, which means it must be exothermic. Correct? If I said I had A plus B plus delta H, it means that I must be getting C plus D. This means I needed to add heat over there. Correct? So this is then going to be endothermic. That's if it's in the reaction. Okay? That's if it's in the reaction. Because I got heat, I added heat here. Okay? So that's a net heat. This is all, remember, delta H is the net amount. Okay? It's after EA. Right? It's what's given out in that very first graphs we looked at in the previous lecture. It's that, right? So what we're doing here is we're saying that when you look at these, just remember that if I've got heat, heat was a product. Heat is a product of this. And obviously from a chemistry point of view, chemical engineering point of view, you need to be able to deal with that heat. You've got to deal with it. Some of it's pretty large, okay? And if I need to add heat as a net heat gain, it means it's endo. If I'm giving it to you like this, all right? If I give you a reaction A plus B going to C plus D, and over here I say delta H less than naught, that means it's exothermic. And if I give you A plus B going to C plus D, and I say delta H is bigger than naught, I mean it is endothermic. Okay? That is referring to the graphs. This one is on the reactions themselves. Okay? That is where heat is given off over there. Now, I want to introduce the term chemical equilibrium to you. All right? I want to introduce, because this is quite a big section. Chemical equilibrium. All right? So, just for the moment, let us think of a kettle. All right? Let's think of a kettle in chemical equilibrium, right? In the kettle itself, I'm going to say it's a glass kettle, all right, like so. And in these are going to be closed systems. I'll explain. Closed systems. Well, if I've got water inside here, okay, we've got water, and then we chuck in some heat. Okay. You know that if we do that and leave it long enough, we're going to burn the pot on the stove or whatever we're using, right? If there's no water in the kettle, it's going to burn out. Now let us do this, which we obviously don't do, all right? We're going to close it. Pretend that, or I don't know if those of you who've got a kettle at home, which has got a glass outer shell. This is perfect to look at, okay? Don't close up the spout, but you can actually look just pre the steam coming out the top at what's happened. What are we doing? We are taking H2O liquid and we are transforming it to H2O gas. This is steam. Correct? That's what we're doing. Now, how do we do that? You add energy. Why? Because the energy is what you need to change the phase from a liquid to a gas. You need to actually break the bonds in the liquid of the H. Remember this from before? And we had a hydrogen bond there, right? Remember it? Put it in green. We had a hydrogen bond over there. This was positive, that was negative. The hydrogen bond requires a lot of energy to break. Because what does it mean when this thing leaves there? It flies. So when this goes off there, we've broken that bond, and then my H2O gas, it means it flies. Now an important thing, once it does that, it's got enough EK, which is a half mv squared. Okay, and we've dealt with this in many cases before. All right? You need to add the mass, you need to get the velocity up. So you've got to add enough energy to make it fly. You've got to break that bond and then it's going to fly out the top, right? Now we've done that. As you watch, you will see over there on the top, you will see little beads starting to form, right? Because what is it doing? It is, whoops, let me write it on the other side. No, it is condensing against the glass. Why? Because it's losing EK. So as it loses EK over here, okay, it no longer flies and it can't fly, right? Like I said to a student the other day, if you run into a wall, you stop, okay? You lose energy, apart from the ouch, okay? You lose the energy. I also did this, all right? Let's just have a look here. What happens? That's what's happening. So my water molecule, boing, it's doing that. It's losing the energy as it's hitting the surface. As it loses the energy, eventually it just sits on the surface. And it regroups like this. It loses EK and stops flying and regroups with other H2O on the side. And essentially, you start doing this. H2O gas going to H2O as a liquid. Okay? I don't know. Okay, H2O as a liquid. So, there comes a point. If you now had it closed, all right, what have we got here? Okay, we have in essence created a pressure cooker. That is a closed system. It can't escape. Granted, you've got a little valve on top that goes every now and again. That's a pressure release valve. But don't worry about that. We're not looking at that at the moment. So what we're saying is this, is that eventually we get to a point where, let me just redraw just the surface of the water. Okay, blue. Okay, blue. So as one flies off, so there we go, H2O. As this one flies, one comes in. So it means that every time one goes that way, one comes in there. That means the system is balanced. For every one that goes, one comes in. Now, in the examples we're going to do with equilibrium chemistry, what is important is bear this in mind. At equilibrium, the rate of that is equal to the rate of this. Okay? So now let's look at this equation of ours once again. Okay, H2O, liquid to H2O as a gas. All I'm going to do is I'm going to change this arrow here to be a like that, which means it can go both ways. And then I'm going to say the reaction that way is called the forward reaction. Why is it forward? Is because I am taking here, let's put a bit of color, I'm taking, these are my reactants, and I'm taking them to products. All right? And at equilibrium, this is my reverse reaction. Isn't it? The forward is always reactants to products. The reverse is always products to whatever. Okay? The forward reaction, forward reaction is my, let's say, my breaking up. All right? Break up. Oh, let's just leave that for a second. Don't worry about that one. We'll get back to it. Just let's conceptually realize what we've got here is that each time one of my waters, okay, comes out. Here we go. Let's use blues. All right, just to keep it nice and topical. So what we're saying is that this is the surface of my liquid. Each time a water molecule escapes with enough energy, another one drips back in. So this process is continuing at the same rate. At the same rate, right? So at equilibrium, okay, at equilibrium, Kevin, you're spelling. Equilibrium, the rate forward equals the rate reverse. Okay? And we're going to get into some of these graphs. But all you need to know is that in this thing, every time one molecule pops out, another one pops in. So if we're manufacturing something, which is where we're heading here, okay? We're heading into the world of chemistry, let's say chemical engineering, where we're going to be manufacturing stuff, okay? Research chemists do it on a small scale, chemical engineers manufacture it on a large scale. So where we're headed is we're now going to start looking at the concept of equilibrium chemistry. I'm going to refer back to this rate of forward, rate of reverse. So let's just recap it. Just in our minds, what are we saying? We're saying that the rate of making it is equal to the rate of breaking it. That's what we're actually saying. The rate forward is making it, and the rate reverse is breaking it. All right? And we've spoken about rates of reactions. They are going to be measured. We're going to get to, in the next one, we're going to look at a few things. Oh yeah, Le Chatelier's principle, we're going to get to that. And we're going to start talking about equilibrium chemistry. This is a fairly big part. So your understanding of this section, okay, it's going to carry heavy marks associated with it. It's also a pretty big part if you understand this, the equilibrium constants, the solubility products, the dissociation, ionization of acids and water. So the whole concept of the pH and everything is pretty much going to be built on this concept, okay? So just go through, maybe if it's not 100%, go through the next one with me and come back to this one so that we understand and we can build on a good foundation for this. Cheers, and I'm looking forward to the next section. Bye.